So good morning, everyone. I hope you are all fresh and rested and ready for our final day of enlightenment about science and instrumentation. All the final classes of the speakers, they save all the best stuff for the last day. So, please.
Thank you. Okay, so today what I'd like to tell you a little bit about is what the science we're most interested in right now at CFA, which is the search for biomarkers in exoplanet atmospheres. And hopefully that'll lead to other great discoveries. And I promise not to repeat the phrase to find out whether we're alone in you. Oh, I said it. Anyway, so turn this thing on. Okay, it's on. So the place to start is the discovery of just extraterrestrial atmospheres by the transit of Venus. As I said before, transits of Venus happen in 8 pairs separated by 8 years and long intervals in between. The next one, as I say, is in 2117. You know, eat vegetarian, exercise a lot, maybe you'll see it. Last one was in 2004 and 2012. But actually, the first historically interesting one was predicted by Kepler. Horrocks and Crabtree actually have observed the transit of Venus. And the really interesting campaign is the 1761-1769 for reasons I'll tell you about in a minute. And then the 19th century transit is when they sort of declared failure of this technique for reasons that'll become clear. So the point is that at that time it was the first, measuring the transit of Venus provided the first rung on the cosmological distance scale. If you very accurately measured the second and third contacts when Venus just had gotten out fully onto the solar disk and then when it left again, from widely distributed global locations, you could actually measure the astronomical unit with unprecedented precision. Now, this required accurate geopositioning. You had to know where you were. You had to know your longitude really well, and you had to know what time it was. So these guys went out and they actually sorry about that. Joseph Nicholas Delisle set up 62 global networks to try and do this for the 1761 transit. This is this beautiful MapMond. It's this huge thing. It's about 3 feet wide. And the red areas were the really good places, and the yellow places were the not. I think the yellow places you could only see one contact. The red ones you could see both contacts, and the green not so good. It's a really beautiful piece of art. So he sent these people out. It was the first, major, not multi-wavelength, but global scientific investigation. And it failed. The 7 Years' War was going on. The French astronomers were on boats that were getting sunk by the boats the English astronomers were on. It was pretty terrible. Some of them arrived at places they were supposed to set up their observatories, and the French had it, and they were English, and they couldn't go. I think one of them was Indonesia, and then parts of India. But the really great sign, like most things, what they discovered was what they didn't think, they didn't even know. I mean, this is the issue of, what will we discover with the GMT? We don't know. And so actually, Mikhail Lomonosov actually found evidence of Venusian atmospheres. So these are drawings from his notebook where he notes that just at the first contact point, the edge of the sun kind of bent out. It made a little ring. And it's written up in this book called Venus on the Venus on the Sun. And nowadays, by 1882, they could actually do photographic photometry, photographic astronomy, and make a picture of this thing. And today, it looks something like this. It's really quite a beautiful thing. And the fact that you see this yellow ring surrounding Venus is evidence that the light from the limb of the star is being refracted around, being bent around. So this is the first extraterrestrial atmosphere. Now, a really interesting point is, and they stopped using this refining this as a measure of the astronomical unit because of the thing called the black drop effect. And people noticed that as the sun approached the limb of the sun, as the Venus approached the limb of the sun, you got this sort of funny little shadow called the black drop. And at first they thought it was because of the atmosphere, but it turns out that this is a transit of Mercury, and it does the same thing. And I found out about this yesterday, and spent some time looking on the web. There isn't a really particularly good explanation, or there are many explanations, and one of them may even be true. So it's probably like a combination of solar limb darkening and the finite, finite point response function of the optics. But you can repeat this experiment yourself. If you take your fingers and kind of push them together, you can make this effect happen, and you can make the black drop effect, and you don't have to wait for the next transit of Venus. Anyway, I mean, one obvious question is how habitable Mars and Venus are. You know, the habitable zone is kind of fuzzy. The atmospheric effects obviously contribute to how warm the surface of Mars and Venus are. The solar luminosity has changed over giga-year timescales really quite a bit. And so, and Mars and Venus, depending on who you talk to, Mars and Venus are almost in the habitable zone. So it's an interesting question to ask. And, also, I mean, the other issues, of course, as we search other stars, where the habitable zone is, has a good deal to do with the stellar type, which is important towards the end of this talk. So is Mars habitable? Well, our atmosphere is 100 times denser, 78% nitrogen, 21% oxygen. Mars has essentially no oxygen. It's almost all carbon dioxide. But nonetheless, there are a lot of extremophiles on Earth. There are things that can live in very, very cold temperatures, things that can live in very hot temperatures. There are extremophiles in the Atacama Desert that essentially live on no water. They live on the dew that forms on salt outcroppings, and obviously can live in extremely saline environments. So as we look at Mars today, I hear endless talks about this. I think the consensus is the stratigraphy of Mars, these layers, the sedimentary, what looks like sedimentary layers, and then the topography that looks like flows on the surface of Mars, mean that at some time in the past there was abundant liquid water on Mars, and some of that water is now still there. If you talk to experts in the field, they will tell you that there's a Lake Superior-sized volume of saline water beneath the surface. And so, when they send probes to Mars now, people are planning to look for RNA-like stuff. On the other hand, if you've ever seen the Arnold Schwarzenegger movie, anyway, I can't remember the name right now. Total Recall, right? Arnold Schwarzenegger finds himself outside the bubble that everybody's colonized Mars in, and Arnold's opinion is that it's not happening. So, yeah, it gets really bad. So, Arnold says, no. The question of Venus. Is Venus habitable? Venus is an even more extreme case. The pressure at the surface of Venus is 90 times the Earth. It has a nasty sulfuric acid cloud layer. It's 500 degrees centigrade at the surface, which I don't think there are no extremophiles now that can survive in those kinds of conditions. It's an interesting atmosphere. The top of the atmosphere, the top of the troposphere rotates every 4 Earth days, and while the planet itself rotates every 243 days. But the thing is that about 4 giga-years ago, as I say, the sun was 25% less luminous, so Venus was very emphatically in the habitable zone then, and it was probably had a lot of Earth-like surface water. But the important lesson is that runaway greenhouse effect at some point evaporated all the liquid water. The liquid water then in vapor phase stays in vapor phase, and what stays on Venus anyway. Something about Las Vegas. So the bottom line is when you have a runaway greenhouse, you're stuck, and climate change deniers take note. The 5th place in the universe to look for exobiotic life would be actually Enceladus, one of the moons of Saturn. And one of the, to me, the most remarkable things that came out of Cassini was the discovery of these jets. They're these jets of water that are spraying out of cracks in the icy crust of Enceladus. And so there's this huge liquid water reservoir beneath the surface of the ice that's tidally heated by interactions with Saturn itself. And so there's strong argumentation being made that we should send a probe to Enceladus to look for life. Ripped from the headlines just last January, some folks actually made an Enceladus-like ocean in the laboratory and found out that at least this bacterium survives really quite well in Enceladus. No, it survives. I don't know whether it likes it or not, but can survive in an Enceladus-like environment. So as much as we understand Enceladus, it could support life. And interestingly enough, they suggest that we could actually colonize Enceladus with these bacteria. What can I say? The one other pitch I do want to make here, I know that there's at least one astrochemist I've been talking to, and astrochemistry is now really, really vibrant. And my wife is also a lab astrophysicist, so I feel. But lab astrophysics is the place to start. This is some work that Karin Oberg has been doing. Methanol, in particular, is very important. It's not a biomarker, but it's a very important precursor to biologically interesting molecules. And the thing is that she's discovered that if you have methane ices that you oxygenate even at like 20 degrees Kelvin, you can actually process that up to methanol. And the other thing that's kind of interesting, so that you may in fact form the first steps of the biological processing, not on the surface of a planet, but in protoplanetary disk. And also methanol survives cometary impacts. So you make a bunch of ethanol in the protoplanetary disk, you put it out in the Oort belt, and then every once in a while one of those comets, remember, comets are probably hydrated the Earth, so they do impact with planets, particularly in early times of the solar system. So you can make it out in the protoplanetary disk, slam it into the planet, and it's ready to go to start prebiotic evolution. So what do we know about planetary atmospheres today? Well, the discovery of a planetary atmosphere was Charbonneau and a bunch of other folks back in 2001, HD 209458b. This is a really bright, incredibly well-studied exoplanet. And what they did is they did HST STIS observations in sodium D, and then they compare the transit depth in the line with that just offline. And so here you see, this is the comparison of inline to offline, and you see that in the sodium D line that there's enhanced absorption. And so since that would pretty good evidence that the sodium is actually in vapor phase in the atmosphere. Remember, the Earth's atmosphere has a huge, substantial sodium layer fairly high in the atmosphere, so there seems to be vapor phase sodium that's evidence of an atmosphere in this exoplanet. The next sort of big step was Heather Knudsen, where she actually discovered circulation in exoplanet atmospheres. She was looking at, I think that I left the HD off. This is another. You see these telephone numbers come up again and again and again. There aren't very many of them, so they're go-to exoplanets. And she was studying the thermal distribution in the atmosphere of this exoplanet and discovered that, in fact, the hottest point is not at the substellar point. You would figure that the place where you were pointing right at the sun would be the hottest point in the atmosphere, but it's actually somewhat displaced. So that's evidence that there's global circulation and redistribution of energy, in particular redistribution of energy to the backside of the exoplanet ultimately. So that's another really interesting result. Mark Swain, 2009, finally is able to measure the presence of CO2, carbon dioxide, and water and carbon monoxide in the atmosphere of yet the same planet again. It's really bright with HST-NICMOS spectrograph. And also notices that in this planet, the temperature decreases with altitude. And the interesting thing is we keep talking about transmission spectroscopy, which is obviously the most favorable way. When the planet occults the star and the light comes right through the atmosphere towards you, the observer, that's optimal. But this was done during dayside observation. So it's entirely possible to study the molecular composition of an exoplanet during essentially its whole orbit, except when it's in its secondary eclipse. X-ray astronomers, again, this same object, really bright. X-ray astronomers, Katja Papenhager, 2013, using Chandra, finds that with the dotted line is the Chandra data, the darker dots are optical data. It appears, this is a really tough analysis, so I do take it with a grain of salt, but it appears that in the X-rays, exoplanets are bigger, which would suggest that there's an exosphere. Like the Earth has an exosphere, which is a puffed up distribution of gas that you don't see optically. This is sort of a cute thing. Are the skies blue on other worlds? And this is a measurement of Rayleigh scattering. Everybody's furiously doing these measurements right now. Rayleigh scattering is, of course, what makes our planet's sky blue. And you come down to somewhere around 9,000 angstroms, and this declining curve turns around and goes up again, presumably scattering blue light preferentially over red light. And the thing is that right now we're all getting ready for JW. This is only possible, I think, for the most part, with HST, which will not live forever. Or if it was going to live forever, when JWST flies, it'll get killed. And so JWST has no capability to make these sorts of measurements. It's infrared optimized. So the exoplanet community is furiously collecting all the Rayleigh scattering data they can now. So anyway, let me discuss oxygen as a biomarker because it is our best candidate. And I'll tell you why. So if we look at the history of the composition of the Earth's atmosphere, it looks something like this. This is something I redrew from a paper by Jim Casting, and it changes all the time. So consider it schematic, and it goes from the beginning of the Earth to 44.5 gigayears ago to the present. Passes through the Hadean era when things were really hot. The Archean, when somewhere during the Archean. Very simple Archean era. Stromatolites start to form. Then Proterozoic is when we start to get diverse life, and then finally the Cambrian, which is sort of the present. And if you look at this curve, you see that what happens is that during the Archean there is life. I mean, stromatolites probably arose sometime 3.5 gigayears ago, but there were all these deep sinks for oxygen. So they made sulfates, I'm not a chemist, and iron oxides. And so as the stromatolites were making oxygen, the iron was turning it into rust and sulfur was turning into sulfates. But then all of a sudden you fill those things up and life gets going, and you see that oxygen 2 and ozone, diatomic oxygen and ozone, start to actually increase at the expense of both methane and CO2. And so, although it's not a unique biomarker, it's not unique evidence of biotic activity on an exoplanet or other element, member of the solar system, it's a really strong indicator that there's biotic activity. The disequilibrium of diatomic oxygen in the Earth's atmosphere is because we're here. Well, not us, bacteria, termites, and things like that. But nonetheless, oxygen is present in the Earth as a highly disequilibrium distribution. It's here because there's life on Earth. Yeah. What's that?
Volcanic activity.
There are, the point is that there are abiotic channels, okay? I get, UV can dissociate things. The bottom line is it won't stay in, if you have a volcanic epoch, it won't stay in disequilibrium. It will equilibrate again. And when it equilibrates, the O2 and the ozone go away. And when I articulated the caveat that it's not unique, when we find, let me just say this, when we find diatomic oxygen, to really sell it, we're going to have to, tell a better story. It's not, the minute you see diatomic oxygen, everybody isn't going to be wholly convinced. It'll have to be a whole story. But certainly this, this would be, a strong indicator, okay? And the only thing is that, I said this as a schematic. The experts always say, oh, well, that's not current. The actual time of the time that the Earth's atmosphere became oxygenated is a moving target. This is, of course, my favorite science journal, The Economist. I always read The Economist and say, that was in APJ this month, that was in MNRAS. And so fairly recently, the time of oxygenation seems to have moved considerably back. So it's a dynamic intellectual environment right now. One thing that people ask, of course, is, are we just practicing the principle of the lamppost? Are we searching for our keys under the lamppost when we're drunk, not because we think we lost them there, but that's where the light is? And so we believe that water and oxygen are essential to life when there are a whole continent of possibilities. And this has been thought about a lot. I mean, one obvious question is, could you make life with silicate instead of carbon? Could you make, replace nitrogen with phosphorus, oxygen with sulfur? And the what I'd like to talk a little bit about is the issue of whether you could replace phosphorus with arsenic. Arsenic's toxic, but koala bears live on toxic eucalyptus leaves. Who knows? And so this has actually been, I think, most conjectured of any of these. There are other possibilities in the periodic table. And actually, there was a sort of a groundbreaking result. Let's see, this was about 6 years ago when somebody looked at, excuse me, looked at bacteria from Mono Lake, which is really, really salty and really, really laced with arsenic, and thought that she had found biota that had successfully replaced, because there was a lot of arsenic, not much phosphorus, replaced the phosphorus with arsenic, and that was a real watershed for everybody. But unfortunately, that sort of fell apart. So right now, we're still stuck with the fact that we can find no evidence that alternative chemistries provide viable biological pathways. So the first detection of this is always cited as the first detection of biomarkers. The famous pale blue dot. Carl Sagan convinced NASA to take the Voyager spacecraft when it was 6 billion miles away, turn it around, and look at the Earth, and made this picture where it was an impressive achievement. I mean, first of all, convincing NASA, and then actually getting the image. They did multicolor photometry that showed that the Earth was blue. The blue color is probably polarization and scattering, but you could possibly link that to the existence of clouds, oceans, forests, and evidence that the Earth was hospitable. Again, the day before yesterday, when I was writing this slide, I really looked through the literature to say, where's the smoking gun? And I don't know whether that's right or this cartoon is a more applicable analysis of that result. That I think is just a lens cap picture. So, but it certainly was an iconic photograph, and it can be interpreted as the discovery of life on Earth. One way you could obviously discover life on Earth would be through aurorae. People don't discuss aurorae very much on exoplanets. It's probably very, very hard to do, but all of the major constituents of the solar system In fact, Saturn, Jupiter all have aurorae. So when you probably don't see a lot of aurorae in Brazil, do you? Come visit me. I'll show you some aurorae sometime. Come in the winter, though. And so the aurorae are predominantly green and then red. And so that's, forbidden transition 5007 is the green and 6300 is the red. So if you saw aurorae, ignoring the fact that there are these lights, you would know that there was light on it. And, but of course, the way we plan to search for it is by transmission spectroscopy. This is a picture from the space station looking back at the sun through the Earth's atmosphere. And the two things that you take away from this picture are, one, you can actually, you can see the Earth's atmosphere. You believe that transmission spectroscopy might work. And the second thing you conclude is it's going to be very, very hard. This disk is very, very big, and the area of this analyst is very, very small. A tough scientific problem. But I hope to convince you it's doable. The last thing to consider is, why oxygen, diatomic oxygen? I'll also try and convince you that it's pretty doable, but it is it's a 21% constituent of the Earth's atmosphere, and it's detectable in A band at 7,600 angstroms, which is an observationally sweet place to work. Methane's produced abiotically quite a bit. I mean, it's 2% constituent of Jupiter and Saturn. So is nitric oxide. I'm not a chemist. Nitrous oxide is very hard to discover, and then all of these other potential biomarkers are probably undetectable. So you don't. This is probably the place. The takeaway here is this is probably the right place to start. So if you're going to look for a molecular oxygen, where would you look? Well, I would argue that the best place to look is in the optical band. That's where observation, highest signal to noise, lowest detector issues are present in that regime. And then there are, in the visible band, there are these three different bands. An A band at around 7,600 angstroms has the strongest signal. So that's probably the place to go first. Has a very nice band head structure. This is, highly regular, nice and sharp, you can really resolve these things out very, very well. If you have high enough resolution, you can really pick it out against the continuum quite well. You like to work at a resolution of at least 100,000. Oh, that shouldn't be 5 million. That should be 500,000. Finger got away from me. But resolutions, and I'll talk about this at the end, resolutions of 500,000 might be a good thing. Although I have ideas about how to do it, but not a demonstrating technique yet. So the obvious question is that here is what do you do, because you're looking for this little tiny signal from the transmission spectrum of that tiny annulus of oxygen around an exoplanet, but there's an awful lot of oxygen in the foreground. So here you see, these are not scaled, by the way. Here is the telluric A-band spectrum of an Earth-like planet. Here's a simulation of the telluric spectrum, the Earth absorption spectrum as you look up at the exoplanet at a zenith distance, an air mass of 1.3, 30 degrees off zenith. And how is it possible? I mean, this is huge. This is tiny. And here the Doppler shift comes to the rescue. All stars that of interest have secular velocities that, when we stare at them, will produce Doppler shifts in those spectra. So when we sit on a moving platform on a star moving in this direction, looking at a star moving in that direction of a moving exoplanet, you in fact will Doppler shift the two spectra with respect to each other. And actually, when you've got lemons make lemonade, this is actually a bonus because you've got an automatic calibrator right in your data. It's just sitting right there. And if you think you found this absorption feature at a certain Doppler shift with respect to this absorption feature, this one better be correlate with that one. And so it's good. It's good that we have an atmosphere on Earth. There are some degenerate situations. Obviously, if you take this whole spectrum and shift it just the right amount, all of these features will line up again. And so, although if you Doppler shift yourself so that this, I can't hold this setting up, you Doppler shift this so that it lines up with the next bandhead structure over, you're in trouble again. And so this, by the way, is all work of Florian Rogler and Mercedes Lopez Morales. I think I had it in the first slide. So you have this sort of complicated structure as a function of relative velocity, where when we have zero velocity with respect to the exoplanet, we don't do very well. And then this is fraction of blends. We do very well at some velocities and then poorly at others. So there's going to be a selection bias based on that. Now, how hard can this really be? Well, the answer is it's been done already, admittedly with a stronger absorption signature. Ignaz Snellen and his group first measured CO in the atmosphere. This is, I think, what's that? Tau. Okay. No, this is an HD number. This is that the Harvard? Oh, HD 209. I'm sorry. I'm not on familiar terms with it. I call it HD 209 458. And so using CryRes on the VLT, which has been down for a while, is CryRes back again? No, not yet. But it's coming back. So this hasn't been exploited very much. CryRes was a fairly special facility. And what you see here is relative velocity. And what you see in this picture are stacks of spectra. So these are just, each one of them is a different spectrum in time order. So what you see is the time sequence of the absorption feature. And there's a lot of special processing going on here. You only see one feature. You don't see the whole bandhead structure because, in fact, he's taken all of those bandheads and stacked them on top of each other to improve the signal to noise. So it's not, it doesn't just, you don't just run IRAF and get the answer. There's hard work involved, but if you blow this little region up here, you see the secular velocity of Tau Boo, I guess now we're friends, and then a simulation, and you know, it's really very much there. So this is done with an 8.4 meter telescope. I'm convinced that we can do, I mean, there's fairly deep analyses that suggest that we can do this with an 25.4 meter telescope. So, I thought that this is a school. I'm sorry for people like Dan that know all this stuff. He told you all about spectrograph design and the diffraction limit, but I wanted to tell you a little bit about spectrograph design in natural seeing. And you know, just one quick thing though, what I'm about to do is step through a lot of diagrams and equations, and nobody's going to be able to absorb it sitting here. But I actually have some notes I've written on this that not only, so put your pencil down, just listen, because you can either go to this address, memorize that. It's a Google Drive, so it's not for human beings. But I can, if you send me email at this address, I'm happy to either send you that link or email them to you, or I'll give them to you on a thumb drive sometime today, but I do want the thumb drive back. So don't panic. It's all written down somewhere. So you know, the first issue is what's the difference between natural seeing and an AO spectrograph? Well, let's just take an example. The MMT is a 6.5 meter telescope, and it's run in a mode where it's a focal ratio f5. It has some other focal ratios. And so in natural seeing conditions, 1 arc second, the size of the seeing disk with 1 arc second seeing is just the size of the seeing disk times the focal ratio times the diameter of the primary, the focal length of the telescope. an arc second is 5 times 10 to the minus 6 radians. You do the arithmetic, and your seeing disk is, you're seeing scale at the focal plane of the MMT, and natural seeing is about 150 microns. On the other hand, if the telescope's corrected with adaptive optics, you're probably talking about something like 10 milliarc seconds, which is 77 nanoradians, which turns out that so that your scale of the focal point is about I'm sorry, that shouldn't be milliarc seconds. That should be about 15 microns. I'm sorry, 2.5 microns, or 15 milliarc seconds. So you're in a very different space when you've got adaptive optics. Life is very, very different. But for the optical band, you don't. Adaptive optics helps, but it doesn't help that much. So the bottom line is that a diffraction-limited instrument can be about this ratio smaller, about 60 times smaller, which means the instrument can be smaller, the slit image is 60 times smaller, and the resolution can be about 6. Or if two instruments are the same size, the resolution would be 60 times higher. So let me just talk a little bit about how a spectrograph works, and perhaps that helps a little bit with Dan's presentation. So what a spectrograph actually does is you have a slit or a fiber that lets light into your instrument and subtracts out all of the surrounding scene in the sky. There's a thing called a collimator. It takes the light and it makes it parallel. There's a disperser of some sort, and that spreads the light out into a spectrum. And then there's a camera, which is a converging lens. And what you get in the end is a monochromatic image of the fiber end that's magnified or demagnified. That's what a spectrograph does. Of course, it makes many monochromatic images across the whole spectrum that it produces. So the determinants of a spectrograph design are the things that play into a spectrograph design are the size of the seeing disk, the size of the pixel of the detector, and the invariance of the A omega product, which I believe Rebecca talked a little bit about, and I won't. And so what really shapes the design are what are the scientific objectives of the instrument, and that mostly has to do with what resolution you want the spectrograph to achieve, which affects the design a lot. And of course, the motherhood statement is that you want it to be as efficient as possible. You want as many photons to land on the focal plane as you can. And so again, as I said before, the size of the seeing disk is usually taken to be at a good seeing site, something like 0.6, 0.7 arc seconds, but with adaptive optics that gets a lot smaller. So this is not a complete listing of science objectives, but given that the resolution of your spectrograph kind of determines where you go with your design, this is something of a recitation of the kind of things you might want to do. Galactic redshifts, you're always looking at the ensemble of spectra of lots of stars with lots of motion within the galaxy, so resolutions of about 1,000 are usually good enough. If you want to do galactic redshifts in the near-infrared band, you want to reject telluric atmosphere, Earth atmosphere OH emission, and so you actually want a resolution of something like 3,000 to be able to identify and throw those things away. And then you kind of step down through these different sorts of things. Stellar abundance people that want to measure the metallicity of, for instance, extremely metal-poor stars, want to work at a resolution of something like 40,000. People that want to do isotope shift studies, hydrogen deuterium, lithium isotopes, need 60,000. Many of the cosmologists want a resolution of 100,000. Exoplanet detection kind of peaks out at somewhere around 110, 120,000. And then finally, the search for biomarkers can be done effectively at somewhere around 100,000, but 300,000 would be good. So, which bunch of these things you decide you want to do with your instrument tells you what the instrument will look like. So the science objective is the independent parameter, and the resolution then becomes the dependent variable. And you have what I call boundary conditions, how heavy you can be, how much money you have, all that stuff. So let me just kind of talk about what goes into building a spectrograph. And so the key property of the spectrograph is the angular dispersion, what sort of disperser you use, how much it spreads out the light. So it's d beta, d lambda. And so if you have a parallel light beam that impinges on a disperser, it will, depending on the properties of that disperser and the wavelength of the light, it will produce some angular dispersion of the beam that comes out. It will separate the colors in angle by that amount. If you actually have a spectrograph, you produce this angular dispersion, but then what you actually measure is on a CCD. So what you, the measured quantity is in fact the linear dispersion. The linear dispersion is just the focal length of the camera times the angular dispersion. And so that tells you physically on your CCD how much your light will be spread out. One factor when you're designing a spectrograph, I'm not going to talk much about this, but it's worth remembering, having the back of your head. Anamorphism is generally thought to be these sort of funhouse mirrors. Victorians love to make these drawings that you put a cylinder, highly anamorphic drawings that you looked at in a cylindrical mirror and it looked like a real thing. In terms of the spectrograph, there's a thing called the anamorphic factor, and that is that if you put a beam of some diameter d into your disperser, the fact that you bend it through this angle beta means that it gets squooshed. So the beam gets squooshed, and when the beam gets compressed in one direction, it actually compresses the image too. So if you have a circular beam going into a disperser, when you get it to the focal plane of your spectrograph, it'll be a little ellipse. It will similarly distort a square slit image. So one question is why not use prisms? I mean, when you're a kid, the first dispersers you encounter are prisms. Usually, if you were going to use it, when you do use a prism in an optical system, you usually use it in what we call minimum deviation, or when it's fully symmetric. So the beam comes in, scrapes the bottom of the prism, and comes out at exactly the same angle, at least for a central wavelength, the same angle it went in at. And the reason you don't use prisms, at least as prime dispersers, is for the following reason. You have to go back to old textbooks, and you look at the geometry of a prism, and you say that the angular dispersion as a function of wavelength is equal to the variation of index of refraction with the wavelength times some mystery factor b. You can't actually, mystery factor b, which you can't calculate. You look it up in a table. This is just the geometry that I use in my notes. So a little algebra, if you want to know the angular dispersion, you do a little algebra, and the most important thing you do is that you expand the index of refraction Taylor series, where this coefficient b is the dominant term, and then more algebra, and you find out that the angular dispersion depends entirely on the wavelength, that factor b that you look up in the table, look up in a table here, and this factor gamma, I should have put this on the same page, the factor gamma is the apex angle of the prism. And so you go to the table and you grind through the whole thing and you calculate the angular dispersion based on these values in a table. These are sort of some typical sort of canonical glasses that might be available to you when you're trying to make a prism. And you find out that in the end, not so good at animation. You grind through some algebra. This is all in the notes if you want to look at them. And you find out that the typical achievable resolution is going to be something like 11,000. Now, I said for an awful lot of science you want to do, really hot science, you want resolution 100,000, resolution 60, 40, even 300,000. This is for a 30-degree prism. You can increase this a little bit, but the number in your head is you're never, in a prism design spectrograph, you're never going to do better than about 10,000-ish with a normal prism. Now, before people had diffraction gratings, which I'll talk about in a second, there were these heroic efforts. These are beautiful instruments, these Victorian, I guess, etchings or engravings. So before diffraction gratings were generally available, you know, they had these things where 6 prisms, and it's actually a double pass, so the light comes in here, goes all the way around, hits the mirror, goes all the way back again, and then there's a complicated mechanism, so if you want to adjust it, these things, this little gizmo keeps them all spaced equally in angle. But of course the thing is that, and this is a straight through thing where they glued a bunch of prisms together, but when you have 6 prisms and a total of passing through 12 prisms, which is 24 surfaces, not much light comes out the other end. You know, every time you hit those surfaces, and they didn't have anti-reflection coatings, 4% of your light goes away. You know, 0.96 to the 24th power, not so good. So nowadays, if we want to build a spectrograph, except for very specialized spectrographs, we use diffraction gratings. And the behavior of diffraction grating as a disperser is governed by the grating equation. It's such a simple equation, but it's so easy to get wrong. So that this m is the diffractive order of that the grating is operating in. This is the wavelength it operates in. This is the distance between successive facets of the grating. And this is the angle of incidence and the angle of diffraction. So if light shines on a diffraction grating at angle alpha, it will, if it's a wavelength lambda, and you're in a given diffractive order, I'll explain that a little more in a second, it will come out an angle beta. And that's just because the incident ray comes in and it experiences this facet is just a little bit behind this facet by this amount d sine theta. But then when they bounce off the grating, this ray is retarded by this ray by amount d sine theta, and so in fact in this case, because this ray is ahead of this ray coming in, and this ray is ahead of this ray going out, you have a minus sign in here, and that for some angle beta that satisfies this equation, you'll get that color light out the other side of the grating. And so I don't expect you to actually absorb all of this, and if you're interested in it, do look at the notes. Whether you choose, which sign you choose for the plus or minus, if you define what we call a grating normal, which is perpendicular to the overall plane of the grating, which side of the grating normal you're on will determine whether that's a plus sign or a minus sign. You can also have transmission gratings. I mean, a majority of instruments are built around what we call reflection gratings. All of this physics applies for transmission grating, where the retardation is produced by the differing optical path length of the grating. And then there is also somewhere way back here, the diffractive orders can be plus or minus, and whether you have a plus or minus sign on the diffractive order determines which side of alpha you're on. So that determines all the different signs of the equation. It is so easy to get that wrong. So I've been talking a lot about diffractive order. Let me just kind of hammer this point in. The point is that for a given angle of incidence alpha, the diffraction grating can in fact just behave like a mirror. So the light can come in and leave the grating at exactly the same angle alpha that it went in at. And no diffraction is happening, so we say that the diffractive order is 0. If m is equal to 1, if it's a first order diffraction, the grating equation is for some given wavelength, some green 5007-03 line will go off in this direction. But of course, it can also go off in this direction, which is shouted for m equals 2 and m equals 3 ad nauseum. So when you shine light on a diffraction grating, it can come off in any number of diffractive orders. Now, your spectrograph is designed to collect light in only one of those orders, so it's if you're don't use some tricks, you'll lose a lot. If you're interested in this diffractive order, if this is what your whole optical system is designed for, the light that's going this order and all can go to very, very high order will be entirely lost to you. So it's really desirable to send most of the light into a single order. And the way you do that is, let me step on to, move on to this slide for a second. The way you do that is that we do something called blazing the grating. And this is a lie, but it's a good lie. It's close enough to the truth so that it gives you the right picture of what's going on. And so if you imagine, if you take a diffraction gratings, as Rebecca said before, are made by taking a diamond and just dragging it across aluminum and making a little groove that's shaped like this, moving the diamond over and making another groove like this, very, very precisely, so they're all equispaced. And each one of these facets here that in fact form the diffraction grating turns into a little mirror. And so light really likes to bounce off that mirror, obeying the law of reflection, where the angle of incidence is equal to the angle of reflection. So if you arrange the diffraction grating so the angle of incidence and the angle of diffraction are exactly the same size as or very close to the angles defined by the law of reflection, most of the light will go into that beam, and not much of it will go into the other beams. So if you take a diffraction grating that's been blazed, you hold it up to a neon lamp or something. A really good example of a diffraction grating, by the way, is a CD or a DVD. You hold it up to light, if it's a real diffraction grating that's been blazed, you look at it and you'll see a spectrum, and all of a sudden there'll be one really bright spectrum. That's the order you're blazed in. So most of the light goes in that direction. And for high dispersion spectrographs, that should be grating up there, we use what are called Echelle spectrographs, which Google Translate, I always thought it meant stairs. Google Translate came back with ladder, but I think Echelle also means stairs. I have no French. And so what happens is that you come in at a very, very steep angle. And so what that means is that you blaze this grating for very, very large diffractive orders. And those are very, very large diffractive orders produce very, very high dispersion. The high dispersion spreads the light out a lot. And so the high dispersion turns into very high resolution. And so Echelle spectrographs with resolutions of 250,000 are pretty doable. Now let me skip. And so that you come to one fork in the road when you make a decision about how you're actually going to feed the spectrograph. You can either feed it with a slit, and so this is characteristic of a slit-fed spectrograph. This is schematically the aperture of the telescope, which focuses light on a little rectangular slot. The little rectangular slot is meant to pass the light of the object you're interested in and mask off all of the surrounding light from the sky or other objects. And it then enters your spectrograph as collimated, dispersed, and imaged onto the focal plane of your camera, where, as I said before, you make a monochromatic image of your slit in many different colors. The other possibility is to use an optical fiber, where basically it's the same sort of geometry. This geometry is the same, but on the other hand, instead of that little slit, the light goes into this optical fiber. It's just a pipe for light. You can have the optical fiber go vast distances, come out the other end, and that's where your spectrograph is. Usually slit-fed spectrographs have rectangular apertures, and fiber optic spectrographs have round slits, although it's also possible and actually sometimes useful to have polygonal optical fibers. You can make optical fibers that are octagonal. You actually can make square and rectangular optical fibers, rectangular, square, octagonal, hexagonal. And a long time ago, I don't think many people build slitless spectrographs anymore, but that's not slitless. So when you design a spectrograph for natural seeing, you have these. This is also true of AO-fed spectrographs. You sort of have have these two choices, and which one you choose does depend a little bit on the science you want to do. With optical fibers, the geometry is entirely defined, whereas with a slit-fed spectrograph, you can actually just change the slit and make it narrower or larger, and therefore select the resolution. Possible to select resolutions in fiber-fed spectrographs, but much more restricted. You can change the fibers, but not arbitrarily. The format's entirely fixed, so that you've got this circle or polygon, whereas with a slit-fed spectrograph, you can have a little tiny slit, or you can have a long slit, depending on how the optics of your spectrograph. Because fiber-fed spectrographs, when you try and do sky subtraction, you have one fiber you put on your object that you're taking the spectrum of your object with, and then you put a fiber as close as you can to see what the sky spectrum is to subtract it from your data. It's never as good as a slit. A slit, you can actually see both sides. If it's not too big, you can see both sides of the object. In fact, the sky subtraction is intrinsically always better. Dan Fabricant just commissioned a slit-fed spectrograph on the MMT to sort of replace a fiber-fed spectrograph, and I think he's going 2 magnitudes deeper, so kind of like that. With fibers absorb blue light, whereas with a slit, you can actually go down to the atmospheric limit. Some people call 3,000 angstroms the atmospheric limit, maybe 3,200. It's very, very hard to get below. You have to work hard to get below 3,800 angstroms in a fiber-fed spectrograph. Infrared is very, very hard. Infrared is enabled in slit-fed spectrographs. On the other hand, with a fiber-fed spectrograph, you have a lot of mechanical independence. You can kind of put it anywhere. So it can have, I think I talked about this a little bit before, it can have very high mechanical and thermal stability because it doesn't have to be in the dome. Whereas the fact that fiber-fed spectrograph, if it's attached to the back of the telescope, bends and is exposed to the ambient temperature of the telescope. Fiber-fed spectrographs or multi-object spectroscopy is essentially built in. It's automatic, whereas you have to work a little harder to make, you can make a slit-fed spectrograph. It's a little tougher job, I think. Just to define what the resolution is, the resolution of the spectrograph, how well it's going to resolve things. There are different ways to characterize this, but in its simplest term, and resolution, as I think of it, is just the wavelength of light divided by the size of the resolution element. So if the slit image in your spectrograph is this wide, corresponding to that wavelength range, at a given wavelength, that's your resolution. You can do this arithmetic if you want to, and I actually do it in gory detail in the notes if you get them. Why do I put up this incredibly boring algebra up here? Is to deliver the most important message of this talk. And if you, with a little bit of algebra and a little bit of insight, we calculate the resolution of an Echelle spectrograph in what we call litro mode. And that's the mode where the light in a given order comes in and hits the grating and comes back at exactly the same angle. It comes right back in your face. And it's a special case I choose, well, I'll talk about it in a second, but the bottom line is that we grind the algebra is all ground out in the notes, and you get this equation says that in litro mode for an Echelle spectrograph, the resolution is equal to the tangent of the blaze angle, the angle you've chosen to make those little mirrors point, times 1 over the size of the slit in radians, times this ratio of the diameter of the collimator to the diameter of the telescope. And this is the takeaway result, at least from this part of the lecture. The reason I choose litro is because it generally yields the highest efficiency, and it yields the highest efficiency, and it also generally yields the highest resolution. I can invent cases where it doesn't. And the point is in this equation, the factor tangent blaze angle is technologically limited. The biggest tangent blaze angle you can have if you go out to buy a diffraction grating is 4. That's it. They don't make them any higher. The natural slit size is set by nature, or how clever your AO engineers are. So, you know, characteristically, the size of the slit is 5 times 10 to the minus 6 radians, about an arc second. With adaptive optics, you do 100 times better. Something like 100 times better. When you build your telescope, you've chosen the diameter of your telescope. So that's kind of fixed by other people. And so the only thing you get to change is the diameter of the collimator. Or you can talk about the diameter of the beam in the spectrograph, how big around the path of light, the parallel light is. So this is the only choice you get to make as a designer. And if you want to increase the resolution, the only knob you've got to turn is that diameter of the collimator. So that means that if you make the diameter of the collimator bigger, you know, the mirror or lens that makes the collimator gets bigger, and all the other optical elements get pretty much correspondingly bigger. So when you make decol bigger, you make the spectrograph bigger. And when you make the instrument bigger, you make it more expensive. And then you hit a technological limit that somewhere around a diameter of 300 millimeters, glass makers start saying, we can't make it that big. So there are ways around this. Some glasses can be purchased in much, much larger sizes, but often having this number be bigger than 300 is going to cost you a lot. You're going to have to do something very special to the design, or think of something very clever, which we always do. But so, as I say, you can get some optical glasses that are bigger than this, but not many. So the takeaway message here is this equation, at least for high dispersion spectrographs, mean that when you build a bigger telescope, you're going to, frankly, spend a lot more money for the instruments. And there's no way around that. So there you go, in big, bold red letters. Big telescopes mean big, expensive instruments. So the Hector shell that we're building, I think I showed you this picture before. You know, this is the telescope is just sort of it's an add-on, an accessory to your instruments. Here's Hector, here's G-Clef, and I think I showed you this before. Dave Charbonneau, Mercedes. It's somewhere in between. So the thing is that many astrophysical programs require resolution of 100,000. Precision radio velocity, a lot of cosmology things around Lyman Alphen, absorption systems, Gunn-Peterson trough. Everybody wants to be up around 100,000. It's very high resolution, very challenging to do that on the GMT. And you can do exoplanet atmospheres at a resolution of 100,000. But what you really want to do is get to a resolution of something like 300,000 to 500,000. And so the question is, what do you do about that? So here are a couple of ideas. One of them I don't think is such a great idea, but I could be wrong. Having said that you violate, you're going to try, if you don't obey that litro resolution equation, you're going to violate the law, the second law of thermodynamics. Here's an example of where I'm going to do that. This is an instrument proposal originating from David Erskine at Livermore. I interact with David, and my name has appeared on some papers advertising this instrument, so it has its merits. And what this instrument does is it's called an externally dispersed interferometer. And you feed the spectrograph with a fiber, and what you do is instead of having a shell grating to do your primary, your high resolution dispersion, use a thing called it's a Michelson interferometer. Basically, any heterodyne interferometer will do, but usually it's been implemented as a Michelson, where you have two different mirrors, and you adjust the difference between those two mirrors to produce phase differences in these beams. The way to think about what a Michelson interferometer does is it produces two virtual images of your slit that are separated longitudinally. And so as you move these mirrors, you effectively move the light sources longitudinally with respect to each other. And then it produces a, you can, depending on the phase relationship of these two mirrors, you can in fact produce very high resolutions. Essentially, if you're mechanically stable enough, there's no limit. The trouble is that it makes a sort of a ring-like pattern with where all of the different diffractive orders are piled on top of each other. So what you do then is you feed it into a standard spectrograph, and you use that to separate out the different colors that are overlapping, and then some complicated lenses to put the light into the slit, because these are a series of donuts, and you want to put it into the slit of your spectrograph. I won't tell you much more about this because it's very complicated. You have to wrap your head around it for a while. But the bottom line is that if you take a solar spectrum and you feed it into the filter comb, the fringe comb of the Michelson interferometer, it produces this very complicated moire pattern. And so as these lines move back, and this is just one way to think about it, the effect is as these lines are Doppler shifted back and forth, they move with respect to this moire pattern that's produced by the Michelson interferometer, and you see motion in this moire spectrum that comes out the other. This is your final data product. It's kind of like Ronchi rulings, if you know that. And so this is a Arcturus spectrum, and this is what comes out the other end of the externally dispersed interferometer. It's a highly messy thing. Now David has worked really hard on this, and actually has developed software to take this pattern and turn it into a realized spectrum. There's some high frequency stuff sitting on top of that spectrum, but nonetheless, you do recover the actual spectrum. The only thing about this is that you have to recover this entire spectrum up to a resolution, in this case, of about 5,000, I think. You have to operate at what they call 8 different delays. So in terms of the Michelson interferometer, you take one spectrum, and this is the moving mirror. You step it one wavelength, take another spectrum, take another one, and then to produce this spectrum that you would like, that looks like a real live spectrum, you in fact have to take 8 exposures. Now, 8 delays means 8 observations. The cost of this instrument is very low. I mean, for an 8-meter telescope, the whole instrument fits in a box that, if it's as big as this podium, that's a big one. And the cost is really low, because you're taking these little bites, and you're not taking very much wavelength. These little bites, you beat out the whole issue of decollimator the telescope. But the cost of observing time is really high. Instead of taking one exposure, it takes 8 times as long. And the observing time, for instance, in the case of the GMT, you would save a lot of money over GClef with an instrument of this type, but you're going to pay very dearly in terms of observing time. As much as I'm being critical of this, the path to 300,000 produces, I think, rich science rewards, and we're not. The book isn't closed on this, so I think it's worth continuing to see how you could improve this. But the bottom line is, I thought I had some notes on this. I guess I took it out. Anyway, I think it's worth continuing to pursue this, but I think there's a better way forward. So I wanted to show you another idea for how to get to a resolution of 300,000 for detection of diatomic oxygen in exoplanet atmospheres. This is work by a guy named Sagi Benami, who works with me. He's the instrument scientist on GCLAB, and he's got this thing called the Fabry-Perot interferometer for oxygen searches, FIOS, which is also what we call our cable feed. Cable television comes through FIOS. All the good things in life. So let me just back up and tell you a little bit about what's that? Yeah. How much time do we have? What's that? Okay, thank you. So first, let me tell you a little bit about how Fabry-Perot works. The Fabry-Perot, you have the light that comes from the focus of your telescope. You collimate it, and you put it into something called an etalon. An etalon is a sandwich where the dispersing medium, I'll qualify that in a second, is this brown stuff in the middle that is going to produce an effect. Let me just say, produce an effect that then you image with your camera under the focal point of the detector. And the Fabry-Perot works on the following principle. If you have that brown sandwich here, and your beam of light comes and impinges on the surface of that material where there's an index of refraction contrast, part of the light is just reflected. And part of the light goes into that stuff, and some of it is reflected at the back surface, and it travels this path of length, optical path difference, delta OPD, and then reemerges some fixed distance later. And depending on how long this path length is, how long how much the phase changes between this point and this point, the interference between these two beams can be constructive, destructive, or somewhere in between, depending. If this path length is exactly some multiple of the wavelength of light at the index of refraction of this material, it'll be constructive interference. So if this is exact after adjustment for the index of refraction, if this is oxygen 5007, and this path length is exactly 10,014 angstroms long, green light will come out in that direction. And so obviously for different path lengths, you create different phase differences. And so as a function of angle, you'll get, it works just like a disperser. Obviously, if you have multiple path lengths, these guys will, if each one of these path lengths is some integral multiple of the wavelength of light in that medium, each one of these guys will interfere constructively, and you'll get a very, very bright beam along this direction. On the other hand, if this is a half integral path length of light, they'll interfere purely destructively. And there's only one thing can happen. If it doesn't come out this side, it comes out that side. So what you have is constructive interference for some wavelengths of light, and the rest of the light will come out the other end. The actual transmission spectrum looks like this. And so this black light is what is the transmitted light. That's the light that comes this way. And so you see that it produces this comb-like pattern, where every, not exactly equispace because of dispersion, but at equispaced wavelengths, light gets through the etalon, and then of course the reflected light, the red light, is reflected by the etalon. And the ratio of this thickness to the distance between these things is a quantity that's called the finesse. Now, what you could do is that this is really, really kind of neat. If you can figure out some way to tell this light from this light from this light from this light, which you can do with a low dispersion spectrograph. But obviously, you'd like to know what's going on in between. So you can take that the reflected light, all this light, and take it and feed it into another Fabry-Perot with a slightly different frequency. And so now you'll have one Fabry-Perot will let this light through, the next Fabry-Perot will let this light through, and this will be the reflected light. And I think you can tell where this is going. If you have stack up a whole bunch of fabric rows, you can actually have a continuous spectrum where the resolution is governed by the width of fabrics.
What about the efficiency?
Very efficient. It is very, very efficient. I mean, if there are no losses, I mean, remember these are little teeny thin slabs of glass, and you go to a coater that can do a really exquisite, and remember you can put a different coating. You can do a really exquisite job. And I'll say the punchline for last. There's one more point that touches on that. So the bottom line is, when you get all done, you can just, for the instrument Szentgyorgyi is considering some number like 8 or 10 etalons. The etalon is the little piece of glass sandwich. For something like 8 etalons, you essentially can kind of have a continuous spectrum. And gather all your information. Now you do have to take this light and put it into a spectrograph to tell this wavelength from that wavelength to that wavelength to that wavelength. What we do is order sorting or order separation. But that doesn't have to be a very big spectrograph because its resolution doesn't have to be very high. And so the way he's accomplished, this is not his latest design, but what happens is the light comes in an optical fiber, sprays out, and all of these are different etalons, and comes out, hits the first one. There's a little tiny polygonal mirror that sends it into this one, and it hits another facet of a polygonal mirror, and it does this and this and this and this and this, and then it goes back into an optical fiber here and goes to low dispersion spectrograph to analyze the output of that. So he has designs that could go up to 1 million. Our target right now is something like 300,000. It's a little easier to do. And the question is that how do we beat this equation? How did we manage to ostensibly violate the second law of thermodynamics? And the secret is that we're only interested in about the 10, 50 angstroms of the A band. We're not trying to do the whole spectrum. If you want to do some other, if you want to do methane, or if you want to build one for the infrared, or you want to do the B band, you'll just build another one. It'll be this big. So what we've done is taken advantage of the fact that because we're working in a very limited wavelength range, we're not bound by this anymore. So a FIOS that operated over 7,000 angstroms, this isn't really the operative equation there. But if it operated over 7,000 angstroms, it would be 700 times bigger, and you'd have a big instrument again. But we only want to look at just these little patches of the spectrum. So we actually have gotten some internal funding to build a pathfinder for the MMT and try it out on some real stars and make sure it really does work. So let me just finish with one thought. My final thought, and that is, what do we expect to find with, we look out and we find life elsewhere in the universe. I jokingly, I'll get to the joke in a second, but I've been thinking about this animal. They're called tardigrades, and tardigrades are incredibly tough animals. They can survive in vacuum for months on end. You can throw them in a nuclear reactor, take them out, and they keep on going. You can desiccate them for 40 years, and they come back to life. And so Avi Loeb, this kind of fine print here, but so Avi Loeb, working with some other folks, I published a paper saying that if there was an Earth-destroying asteroid, that tardigrades would survive. I'd like somewhere down here, he said, he tries to, well, let's say, he tried to kill his tardigrade. So it turned out that when this hit, this was Washington Post. It hit the news in a really big way. Now it turns out that, well, we go to this slide here. the tardigrade had previously been selected as the GCLAF mascot. You know, they're national birds and state birds, and so this is, you know, we have a bunch of swag with the GCLAF logo and a tardigrade in it. And so I was actually able to, I had some pet tardigrades, which I'd taken pictures of on this laboratory microscope we have. This is one of my pet tardigrades, and I brought it. When I saw this on Gizmodo or something, Avi, here's your own pet tardigrade. So I brought him one of these, probably not one of these, but I brought him some pet tardigrades. And so the tardigrade is in fact the GCLAF animal, because, you know, when we look for life on other worlds, the life that's looking back at us will probably be tardigrades. So I'll stop there.
Thank you very much. Questions? Questions, everyone?
Let's say you're looking for life in exoplanets. We look for life as we kind of know it, so we look for rocky planets. But suppose we have this case, for example, of Encephalus, where there's a moon which is rocky.
Yep.
And so should we look for example, gas planets that will be in the habitable zone, because their chemistry, their atmosphere will be different from the moon's atmosphere, right? So how do we look for it in moons?
Look for it in a moon, or
yeah, I don't know if
or in a
look
gas
for
planet.
it in moons.
Well, Enceladus, you know, Enceladus has it's a well, first of all, I'm not a biologist. I don't think about these things that much. The standard thought is that a planet must have a surface. That you have to, if you just take the stuff, either the prebiotic stuff or the early phase stuff, and it's dispersed in a volume, you'll never achieve the concentration necessary or the gradients necessary to move prebiotic evolution along. So a surface is necessary. The ocean on Enceladus is a shell. It has a core. I don't know. I haven't been there yet, but I've been told by people who haven't either that there's a core, and so that there is a surface on which, you know, you could work on. You know, you can deposit or sediment stuff out, and hopefully that becomes the stuff of life. But in purely gas planets, the feeling is that you're just never going to get either the gradients or the concentrations that are necessary to drive prebiotic evolution.
But for example, if we find an exoplanet by the transit method,
yep,
with a star, can we find a moon of this planet with the same method? Like, can we really analyze this moon, or is just like too tiny?
Can we find a moon?
If we find moons around with surfaces around a gas planet.
There's the guy that thinks most about this is David Kipping, who's at Columbia, and he has everybody morally convinced that with good enough data he will be able to find moons. Yes, haven't done it yet. Maybe microlensing data is the right place to start. I don't know, but you need really good photometry. But it's not. I think in my first lecture I showed that Kepler has discovered moon-sized exoplanets. So you're going to discover moons probably as the system crosses the limb of the star, and so it's not going to be, if the transit has a photometric signature like a, sort of square wave, you see the moon as it between first and second contact and third and fourth contact.
So one thing that you probably explained and I couldn't understand. So GCLEF is designed for natural scene.
Yeah.
But eventually it will operate under AO, even that AO is not that good on optical. So
I didn't talk about this a lot. It was something I threw overboard. GLAO will help, first of all. But glad you asked that question. That's a really good question. We've done some modeling that would indicate that as AO gets better, it helps with fiber-fed instruments. So usually you characterize adaptive optics by the Strail ratio. Now, how much that peak is in the middle. And below something like 8,000, I'm not a scholar of adaptive optics the way Rebecca is, but somewhere around 9,000 angstroms, you don't help that much with the Strail. But we've got this optical fiber, the AO point response, the diffraction limit, it's like, if it's 2 microns, our optical fiber is 60 times larger. And so as AO gets better, it concentrates more light in the sense of getting light into a circle. You do better with AO, the models say. So that all the way down to 4,000 angstroms, you in fact double the amount of, you can, the models say, double the light that goes into your optical fiber. So you made the GMT into a effectively for us, a 33-meter telescope, which is really, really great. So, but I said the models. Now, NEK has been working on the next step. The next step is to go to a telescope and try it out and see whether the models are right or not. The only telescope in the world that I know of, remember, adaptive optic systems all feed infrared. And so Magellan actually has a place where they have the adaptive optic image come out in the optical band. And we would like to go to Magellan and put an optical fiber in that system and turn it on and turn it off and see how well it does. But that's kind of expensive. A team of 4 people have to spend a couple of months preparing the experiment and then go and do it, and then it doesn't work and you have to go back again, so it's a big effort. So NEK has been working on an intermediate thing. You can buy laboratory simulators of turbulence from natural seeing, and then other, let's say, change the optics a little bit, this little disk, and then you can simulate AO correct. You could any level of AO, GLAO, extreme AO. And so he's doing the laboratory experiment to see whether, if it doesn't work in the lab, it's probably not going to work on the telescope. So that's happening right here, right now. And we're going to meet tomorrow and discuss the data. So thank you for asking.
Great, thank you.
Can you remind us what is the size of the fiber of GCLEF?
GCLEF operates in a couple of different resolution modes. I can tell you what the angular size is. There's we call the medium resolution mode. It's a resolution of 35,000, and that's tuned for stellar abundances, not flavor of stellar signs. For people who aren't too picky and only want a resolution of 20,000, there's a 1.2 arcsecond fiber. Seems not so good. You're just always going to get more light in the fiber. To get resolution 100,000, we actually, when I said you had to do either spend an extraordinary amount of money or use extraordinary means, to get to resolution 100,000, we couldn't build a spectrograph that would do that for a finite amount of money. So what we do is we actually, after the light arrives at the focus of the telescope, we break it into, basically we break the pupil up into each one of the individual 8.4 meter primary mirrors. That's why, for that kind of stuff, the GMT is so much better than the ELT or the TMT, because they're circular fibers, and if you put that circular pattern on a filled aperture, you're going to throw a lot of it away. But so there's not too complicated, but reasonably complicated. So what we do is to get to resolution of, it's actually 108,000, at least at some wavelengths, we treat the GMT as 7 independent 8.4 meter telescopes. So we'll build it's the equivalent of building a VLT instrument times 7. So it all fits in the same box.
And in terms of how expensive it is to discover a planet, what I'm thinking of is the 3.6 in La Silla is given because of Hubs, it basically doesn't do anything else.
Right.
And it's, you know, everybody's thankful for that because basically that's what's keeping La Silla alive. How much time does it, or rather, how much telescope time is it needed to discover a planet? And in that sense, how much time of GMT is going to be taken over
All of it.
planet
All of
finding?
it. All of it.
That's what I was expecting.
Rebecca's not even listening. What? Well, okay. A couple of things. One of them is the current plan is will be the first light instrument. So for a while, we'll kind of, we may not be. I mean, between now and first light, things can change. But in principle, we're the first light instrument, and so we should be able to do some of the stuff. It's incredibly important that the GMT be able to change instruments efficiently, okay? And because, you know, in theory, you really could learn all about exoplanet science in 2 observations, right? You know, 1, 2, you know, if it's transiting in particular, you know where quadrature is, you go bang, bang, 2 measurements. And that's where the good data really is. So if we can switch instruments rapidly, and somebody says, well, you know, now I need 40 minutes, take the data and go back to GMAX or GMT mirrors or something. If it takes an hour to change instruments, it's a different world. So I think the plan is, well, I know the plan is, whether it happens or not is, you know, sometime, it's still in the future, but the plan is to be actually, at least for the instruments that are on the, you know, on the instrument platform, not the Gregorian instruments, is our goal is, our specification is to be able to go from one instrument to another in 15 minutes. So it's kind of a hit, you know, but for a really important thing, you'd be willing to do it in the middle of the night. You have to be, we got to do it, be able to do it in the middle of the night without killing ourselves. Okay?
So, yeah, if I could just comment on the instrument changing. So remember we have one location, the direct Gregorian focus with that big cylindrical cage that's underneath the focus. The large spectrographs right there, we probably won't be changing them from during the night. We could easily change them from one night to the next. But that means you'll have one large spectrograph mounted that's appropriate to the moon phase, either optical or near infrared. The smaller, the single object spectrographs are all fed by a tertiary mirror. That tertiary mirror will move in and out of the beam of the telescope very rapidly, and it can rotate simply to redirect the beam to any of the instruments on that platform that is at the top of that cylinder that's the Gregorian instrument rotator. So Andy's instrument G-clef will be fed by a tertiary mirror off on that, so that it's one of the instruments that's rapidly accessible, and the other single object spectrographs as well. So we should be able to move between instruments in 15 minutes at most. 5 minutes is the goal for the single object spectrographs, and if you just pull the tertiary out of the way, you can go straight down to the large spectrograph. So it should be very quick to move between instruments, and that is not just that not only makes it efficient to do observations that need high cadence, but it also makes it efficient to schedule by queue or whatever's appropriate.
And of course, there's always the possibility with Manifest of having both GMAX and G-clef being fed simultaneously, so there's 0 time required to do it. And so that's actually quite an interesting option for some of these things that require short, sharp observations. You put some G-clef fibers out on the manifest field plate, you're doing your G-max stuff most of the night, and then you go and do the G-clef observations with 0 time loss.
That's right.
You mentioned that the jury is still out on whether Earth extremophiles could survive on Mars. And it seems to me that that's a question we should be able to answer in a laboratory experiment. But now that I'm asking my question, I'm thinking maybe you meant to say the jury is still out whether extremophiles exist on Mars.
Well, the jury's out as whether they're there or not.
Yeah.
And we don't really know what the salts are. I mean,
The soil composition is a problem, I think.
I mean, you know, there is a... The solar system science community is absolutely certain. You know, the story is ironclad. It's just that no two people tell you the same story. So, but you know, the bottom line is that NASA has always talked about, you know, in their exobiology programs to follow the water, and for a long time they didn't really think there was water on Mars, but the consensus is now pretty much that certainty in science is rare, but as close as you get to certainty that there was a lot of water in the past, and when you read the papers, they're absolutely convinced that there's a large reservoir under the surface, but you know what it looks like, you know, whether you were required to have surface biota that then populate that subsurface reservoir, I don't know. But anyway.
So we can address the question in a slightly different way. There's a huge difference between having a large population of single-celled creatures and gradually changing the conditions to Mars conditions and dumping a relatively small population of unadapted creatures into the same environment and seeing what happens. Evolution works, in spite of what they say in the United States. And so it's very difficult to do the experiment you want to do. Simply taking extremophiles and putting them into Martian conditions will not tell you the same thing as taking a vast planet-wide population of extremophiles and over a period of hundreds of millions of years moving from more favorable conditions to Mars-like conditions. It's not at all the same thing.
More questions? If not, let's thank Szentgyorgyi again.
Thank you.